All right. So our speaker today is Ben Steinberg, and the title of his talk, as you can see there, is Partial Actions of Free Groups and Groupoid Homology. Please, Ben, go ahead.
All right, thank you for giving me the chance to speak here, and it's good. It's good to be speaking at the seminar again with our new interface of Google Meets. We'll see how this goes. Um, so this is a topic that I've been thinking about groupoid homology a lot recently, and this is not necessarily the deepest of results, but the idea is that maybe some things that were done in more complicated ways can be done in more simple ways. So that's kind of the approach that I'm taking here. Um, so let me just sort of start with the motivation. So as people probably know, étale groupoids are nowadays pretty central to the study of C-star algebras, and also rings are becoming more popular. And people have been interested in the homology of these groupoids, both as invariants and because the homology can connect to things like the topological full group. But if you look at many of the papers, even for the most simplest of groupoids, they end up using difficult results, either things like some version of the Linden-Hochschild-Sayre spectral sequence for a cocycle, or some other fancy techniques, and not really direct elementary ones. So my goal here was to find for at least a class of nice groupoids a projective resolution of the trivial module that you can really write down. Um, I guess if you go in more a little bit more generality, I think you can make everything work as a flat resolution, but I really focused on projective because of one of the applications. Um, and so what I'm going to get for these partial actions of free groups is a resolution of length 1, so a very short resolution. And that makes the homology very easy to compute because the resolution is short and it's explicit. And I also use it to compute the global dimension of these algebras of the groupoid algebra over a field. Um, so let me start off with what are partial actions. So partial actions were, I think, introduced into the subject by Hui Axel quite a number of years ago now. Originally, they were of interest in the context of C-star algebras, but they also make sense for rings. Well, I mean, they're not really, I mean, the algebras associated to them. Obviously, partial actions are about groups. So what is a partial action theta of a group on a space X? So you have a bunch of open sets X sub G, one for each element of your group. You have a homeomorphism theta G from XG inverse to XG. So XG inverse is the domain of G, and XG is the range of G. It maybe takes a little time to get used to this. When I give one motivating example of partial actions at the end, then maybe the reason for the notation will be a little bit clearer. And then there are some requirements that are here. So one requirement is that the domain of the identity and the range of the identity should be the whole space, and the identity should act as the identity. Number two is theta of G inverse should be theta of G inverse of the function of the homeomorphism. So notice that the inverse of this would go from xg to xg inverse, which is what you would want. And the third condition is a little bit messy to read, but basically what it says is if theta g theta h of x makes sense, then theta g h of x also makes sense, and they agree. So if the left-hand side makes sense, then the right-hand side must make sense and agree with the left-hand side. That's what this is supposed to say. Hopefully I got that correct. And in this talk, we're going to always assume that X is locally compact, Hausdorff, and totally disconnected. And I'm also going to assume in this talk that the XG are clopin. That's not really necessary, but it's convenient for what I'm doing because it will guarantee that the continuous functions with compact support on XG have an identity, and that makes life a little bit better.
So sorry, so you do not require the XG to be compact.
Well, in a moment, X will be compact anyway, so,
Okay.
but it's not really strictly speaking necessary. If you're working in the locally compact Hausdorff and totally disconnected case, then XG clopin will still have an identity. So it's sorry, it won't have an identity, but we'll have local units. Sorry, we'll have local units, which is fine. And the local units are coming from the original algebra. And maybe it's not so important. I'm going to be having everybody compact in a moment anyway. So a typical example, maybe the motivating example, is if your group acts on a space Y and X is clopin, you can restrict the action of G to X. And in this case, the domain of G will be those things in X, which when you hit them with G, stay in X. So X intersection G inverse of X. And I think that's probably the motivation for using XG inverse in this notation. At least I assume. I mean, Hui's the one who introduced it, so he would know better, but that's my guess as to what the meaning originally was. Um, so this is a partial action. I mean, I guess this is a bit quick if you've never seen them before, but you should just keep in mind this idea that they're basically what you get if you restrict the total action to a subset. And in some sense, if you don't care about properties of your space, you can always get it this way. But the problem is, even if your space Y X is nice, the space Y that you construct so that this works may be terrible. So that's why we just define it intrinsically. So in this talk, I'm going to be interested in partial actions of free groups. So FA will be the free group on a set A. And X will introduce a notion of what's called the semi-saturated partial action. What it basically means is that if a product U times V is reduced as written, so in other words, there's no cancellation when you take the product of U and V. So in other words, the length of UV will be the length of U plus the length of V. Then the action of theta UV is the composition. So what this says is it works like a regular action as long as the product is reduced. Okay? So why is this special? Because these kinds of actions are completely determined by what the generators do. So you tell me what the generators do, and then given any reduced word, this condition here tells me how the reduced word must act. And Excel proves that if you do the obvious definition of how a reduced word should act to meet this condition, then you do get a partial action. General partial actions of free groups are not determined by what the generators do. They can be ugly. But if you put this extra semi-saturated condition, which most examples in practice have, then all you have to do to specify the partial action is tell me what the generators do. And we're going to take advantage of that because that means we can define these kind of actions very easily. And another notion that Excel introduced that I'm going to just throw in here is orthogonal semi-saturated actions. I mean, the definition of orthogonal doesn't care about semi-saturated, but I've only seen people look at it in the semi-saturated case. So with the orthogonal action just means that the ranges of the generators are pairwise disjoint. Is the sound not coming?
I'm sorry to bother you. One question.
Sure.
Why? So in the definition of a partial action, you do require that the product goes to the composition.
Not exactly. That was the bit where you have this messy formula. The product is the composition when the left-hand side makes sense. This condition here says that the left-hand side makes sense. X is in the domain of H, and when you apply theta H, you're now in the domain of G.
Okay, so you're requiring that in the second slide, you're requiring that this happens automatically whenever the two elements are letters or words.
So whenever there's no cancellation. So like if I do AB times A inverse B, I expect them to actually be a real composition. But if I did AB inverse times BA, there's cancellation, and I don't expect this to hold.
Okay.
So when there's cancellation, then the product could have a bigger domain. So in general, this condition 3 says that theta GH inverse can possibly defined even if the composition isn't. So theta GH has a bigger domain than the composition. But if G and H have no cancellation when you take the product, then I require them to have the same domain and be equal. So it looks like a technical condition, but Hui uses it a lot. If you look at his book on the partial action stuff, the semi-saturated condition appears a lot. It's something that makes everything behave better, not just for partial group actions, but like these fell bundle stuff and things that I don't know much about. But he likes this condition, and it's certainly convenient for us. For me, the main thing that's useful in this is that if U is a prefix of a reduced word UV, then the domain of theta u, I'm sorry, the range of theta of u is contained in the range of theta uv. So normally with a partial action, the range of theta u would not have to be contained in the range of theta uv. But if the product's reduced as written, then it does. And that's what ends up being what I use in the paper the most. Okay, and then this orthogonal condition just says that the generators have disjoint domain. If you want an example of an orthogonal partial action, I probably should have written this as a slide. Take the shift map on the Cantor set. So take the shift map on the two-element Cantor set. Then you can define a partial action of the free group by saying that, let's say it's a Cantor set on 0, 1. Then you can define a partial action of the free group on 0, 1 by saying that 0 removes, the generator 0 removes zeros from words that start with 0, and the generator 1 removes 1 from words starting with 1. And then actually I wanted the opposite. Sorry, I said it backwards if I want it to be orthogonal. I actually wrote down the inverses, so said the inverses. Sorry, say it again. I'll say it again. You can have a partial action of the free group on 0, 1 on the Cantor set 0, 1 to infinity by saying that 0 adds a 0 to the beginning of a word, and 1 adds a 1 to the beginning of the word. Then the range of 0 are things starting with 0. The range of 1 are things that start with 1, and those are disjoint. And this will give you a semi-saturated action, and the inverses act the way I said a second ago, as the inverses to the shift. So if you have a partial transformation groupoid, so if you have a partial action, there's a transformation groupoid. It's defined like the regular transformation groupoid, except you restrict to pairs g comma x so that x is in the domain of g. So that g of x theta g of x makes sense. And you give this the product topology and then the subspace topology. So I look at all pairs g comma x where where x is in the domain of g. Remember, xg inverse is the domain of g. So the unit space of this groupoid can be identified with x. The source of an arrow g comma x is x, and the range of g comma x is theta g of x. So you can let g act on x, and my condition here says that theta g of x makes sense. The way you compose two arrows, in order for this to make sense, this guy has to be theta h of x because that's where this arrow ends, and then I just multiply the g and the h. So it's just like the transformation groupoid, and the inverse of gx is g inverse theta g of x. So it's just like the transformation groupoid, except that we restrict with the pairs that are allowed. This construction was introduced by Abadi in his PhD thesis. And this will be an ample groupoid if X is locally compact, Hausdorff, and totally disconnected, and my domains were Clopin, like I was assuming. So let me give an example of partial transformation groupoids, which are Deaconu-Renault systems. So Deaconu-Renault systems are very popular among C-star people. Graph groupoids are examples of Deaconu-Renault groupoids. So a Deaconu-Renault system consists of a space X and a local homeomorphism from an open subset of X, which I'll just call domain T, to X. Originally, it was from X to X, but people have generalized it. There are examples where it makes sense to use a subset of X, like when you have graphs with either sources or sinks, depending on and infinite emitters, depending on or infinite receivers, depending on your conventions. And Hui Axel and I showed in a paper in 2019 that if you're given an orthogonal semi-saturated partial action of a finitely generated free group on a stone space, so stone space just means compact, totally disconnected, and Hausdorff. So now I'm putting compact in. It's not strictly speaking necessary, but it will make life easier later on, especially since I would like to have finitely generated free groups. The finitely generated free group does need this to be a stone space, otherwise you'd need an infinite one and you would need conditions on the space. So to make things smooth, I'm just saying that we have this. So we have a semi-saturated orthogonal partial action of a free group on a stone space. Then you get a Deaconu-Renault system by making T the union of the theta A inverses. So remember, orthogonal means that the domains of the XA's, which are the ranges of theta A, and these are the domains of theta A inverses, are disjoint. So the domains of the theta A inverses are disjoint, so I can glue them together to a single local homeomorphism. These guys were all homeomorphisms, so they restrict to homeomorphisms on these sets, so it's a local homeomorphism. And because this is a finite set, it's a finitely generated free group, this is a finite union of clopin sets, so it has a clopin domain. And we proved that the partial transformation groupoid is the usual Deaconu-Renault groupoid, which I did not define because it's a little bit complicated. If you haven't seen it before, I don't think putting a slide defining it will say that much. You can take as the definition just being this partial action groupoid because they're isomorphic in this case. And so I sent Gilles G. Castro an email asking him if the converse was true because I thought it was true. And he wrote down a proof, so which he let me include in the paper. If you have a Deaconu-Renault system with X as stone space, so that means compact, Hausdorff, and totally disconnected, and the domain of T is clopin, then there is a partial action orthogonal semisaturated of a finitely generated free group, so that your T is this guy here. And so basically every groupoid of a Deaconu-Renault system where X is compact comes about this way. If X is not compact, but it's second countable, you can still make it work. But if you start running into spaces which have bad topology, like not paracompact or stuff like that, then you have trouble making the ranges disjoint. So you need some conditions here. And you also have to lose finite generation of the free group if the space is not compact. But anyway, there is something you can do under some assumptions when X is not compact, but it's more technical. So for the moral of the story is that Deaconu-Renault systems with clopin domains on compact spaces are the same things as semi-saturated orthogonal actions of partial actions of free groups on compact spaces. Of course, there are plenty of actions which are semi-saturated and not orthogonal. For instance, a total action of the free group is semi-saturated, right? If you have a total action of the free group, then it's semi-saturated by it's better than semi-saturated. It's not orthogonal because all the guys have range the whole space, but it fits into the theory that I'm doing. And I should point out, Deaconu-Renault groupoids include the graph groupoids associated to graph C-star algebras and Leavitt path algebras. Okay, so now I'm going to remind you what is a groupoid ring. So let X be a locally compact Hausdorff and totally disconnected space. If R is a commutative ring, then I'm going to denote by Rx the R module of locally constant mappings from X to R with compact support. This notation is used by me and is getting more popularity, but it's still not universally accepted. If X is a discrete space, then this is a free module on X, so I don't think it's completely unreasonable. And I don't use the locally constant mapping with compact support notation because when X is not Hausdorff, which is not the case here, then that notation doesn't really make sense. So anyway, this is the notation I use. I know it's not 100% popular.
You just said about the X is Hausdorff.
I'm sorry? Yeah, here X is Hausdorff, so it would be reasonable to use CCXR. But since I often work with non-Hausdorff stuff, I don't like to use it. In this talk, everybody's Hausdorff because the partial action transformation groupoid is always Hausdorff. The Deaconu-Renault groupoid is always Hausdorff, so there's no non-Hausdorffness here. This construction Rx is functorial with respect to local homeomorphisms. If you have a local homeomorphism from X to Y, you have a push-forward map from Rx to Ry. What you do is you sum the values of F on the pre-images of Y. That's how you determine the value on Y. Because F is locally constant with compact support, and phi is a local homeomorphism, the fibers are going to be discrete, and therefore the fibers will intersect the support, which is compact in a finite set. And so this is a finite sum. So all the sums that look infinite are actually finite. And if your groupoid is ample, then RG is a ring with this convolution product. In fact, the convolution product is in some sense the push forward of the multiplication map on the groupoid. Once you identify RG cross G with RG tensor RG. So it's kind of the multiplication I eventually realized is sort of a special case of this. although the identification with the tensor product may not be so trivial, but it's true. Okay, so this is the groupoid ring. Now, in the case of a partial group transformation groupoid, the transformation groupoid associated to a partial group action, you get a partial skew group ring. Now, I don't know how familiar people are with partial skew group rings. It's a generalization of the standard skew group ring. So, a skew group ring, you have a group acting on a ring, and you form something that looks like a semi-direct product, or in C-star algebras, you call it the cross product, but in ring theory, it's called the skew product. And so this partial skew group ring is the ring theory analog of the partial cross product. In ring theory, cross product means something different than this, so there's not completely accurate terminology between the two fields. So suppose G has a partial action on a stone space with clopin domains. So I want compact again so that I have a unit, and so that everything I write down makes sense. So inside of the algebra of this groupoid, I can take the characteristic function of G cross the domain of G. So this is an example of what's called the bisection of this groupoid. So xg inverse is clopin and x is compact. So xg inverse is compact. So G cross xg inverse is compact. And it's also open because xg inverse was clopin, and this is the product topology. So this is a legitimate guy in my algebra. It's the characteristic function of a clopin subset, of a compact open subset. So it's a completely legitimate guy, delta G. And you have a direct sum decomposition as an R module into Rxg. So these are the functions defined on the range of G times delta G. So every element can be uniquely written as a sum of a function defined on the range of G times this characteristic function. And the product looks a little bit like a skew ring product, but you have to be a little bit more careful when you do a partial skew group ring. So this is the formula for multiplication in a partial skew group ring, where remember the lower star is the push forward. Since these are homeomorphisms, the push forward does what you think it does.
So sorry, is this? I mean, if I take r of x as you defined it before, right? So you have a partial action of G on r of x.
Yeah.
And this is, I remember from Rui's monograph, inverse semigroup and combinatorial system, where he defines the product he defines the cross product of a semigroup action on an algebra, and the formula looks very much like this.
Yeah, this is also the formula he uses for the partial action, group action cross product, which is, I guess, probably a special case. So yeah, so this is the formula that's used in the partial case. The reason for this formula is that the domains of each, in the partial action of G on R of X, the domains are two-sided ideals. And this product here forces the domain to be inside where theta of G star is defined. So this product, if I just try to do theta G on B, it's not defined. But if I multiply B by this element, then it goes into the ideal of things on which theta G star is defined. Theta G star of B itself doesn't make sense. If it was a total action, then this would just translate to being A times theta G of B. But that doesn't make sense in the partial setting. So I have to take this product first to get to something which the outside guy is defined on. So this is isomorphic to the partial skew group ring, if you're familiar with partial skew group rings. And this is why Abadi introduced this groupoid, but he was doing it in the C-star context. I'm not sure who first wrote this down in the ring theoretic context. If you know the C-star algebra result, it's fairly obvious. It might have been Daniel Gonçalves, I'm not sure. But it's basically the same proof as the C-star case, except there's no completions to worry about. So now I want to talk about groupoid homology. So there are a number of ways to define groupoid homology. I'm going to do it by imitating group homology because this is the approach that I use in the paper anyway. So I'm going to define the trivial left R module, RG module, which is just RG0. So it's the locally constant functions on the unit space to R with compact support. And then this is the module structure. All right, what is this? The way to think about this? You can think of H as being a function on the unit space. So think of it as a formal linear combination of elements of the unit space. And then an element G of the groupoid should just move an element of the unit space that's its domain to its range. And so what this, and then the function f is a linear combination of groupoid elements. So what this is doing is you're taking a linear combination of groupoid elements, you act on a linear combination of units by basically having each element of the groupoid take its source to its range. That's what this does. But I have to write this as functions, not linear combinations, because it's more general than linear combinations. But that's what this is doing. So if this was a discrete groupoid, you could just define the action by saying, all right, each element of the groupoid takes its source to its range and then extend linearly. If this was a discrete groupoid, that's what it would be. If you have a group, if you have a group, then the unit space is trivial, and so you would just get R. And this action taking the identity of the group to itself just means that you're not doing anything. So it's a trivial group action. Similarly, there's a trivial right module action. In the trivial right module action, each groupoid element takes its range to its source. And so here's the definition of groupoid homology. If you have a left ZG module, then Hn of G with coefficients in M is Tor from the trivial right module to M. And the homology of the groupoid is Tor from the trivial left module to the trivial right module. So it's the same definitions as in group homology, except we have a different and more complicated trivial module. So I'll give this a moment to sink in. So there are explicit chain complexes which compute this homology. There's like a bar resolution, and then there's like a bar complex that you can find like in Matui's paper. I guess it was Mordic and McCrinnick who first defined homology theory for general étale groupoids, but this is what it boils down to for ample groupoids. And I think that this allows you to kind of use groupoid ring approaches to try to understand the homology, because now you're just doing ring theory instead of having to do some fancy groupoid stuff. And so we can define the cohomological dimension of G as the minimum length of a projective resolution of the trivial module. It doesn't, ZG0. It doesn't matter whether you do left or right. I should point out this is integer coefficients, right? Because I took ZG0 and ZG. So this is trivial coefficient. This is integer coefficients. You can do homology with more general coefficients, but anyway, that's what we do.
Sorry, since you are dealing with rings with local units, but not necessarily units. When you say M is a left module over
it should be unitary.
Okay.
And then everything's in the abelian category with enough projectives and enough flat modules, and everything is fine. I mean, the particular groupoids I'm looking at in this talk have compact unit space, so they have identities anyway. But yeah, I'm slightly, yes, you should say unitary left modules. Yeah, for this to behave well. But in any event, the projective modules are unital, and so are unitary, and there's enough projectives, and so everything is fine for doing homological algebra. So now I'll tell you what is the projective resolution for a semi-saturated partial action of a free group on a stone space. And to get things to be projective, I really need this to be compact. So that way the elements I write down are idempotents. So here's the short projective resolution of the trivial module. So the unit space for this guy is just x. So I'm calling this zx instead of zg0. G0 is x. So what is the module? So here's zx. That's my trivial module. Then I take the ring, which is a projective module because it's unital. I'm assuming it has a compact x, compact unit space, so it's unital. Then I take the map induced by the range map. Range map is a local homeomorphism, so it induces a map. And then I take the direct sum of ZG times 1XA. So 1XA is an idempotent. XA is a compact open subset, so it's a bisection. I can take 1x0, and that's an idempotent. And so this is a projective module. And so this is a projective module, and one has to show that the sequence is exact. So Zx here is a trivial module. R star is induced by the range map, and this is how the boundary map works. on the A component, so the component corresponding to A, I multiply F by that guy delta A and I subtract F. Remember, delta A was, I'll just go back a second. Delta A was, where's delta A? Oh, delta A is the characteristic function of A across the domain of A. That's what delta A was, in case you've forgotten. So that's the guy I use. The way I think about this is basically I'm imitating the free resolution or the projective resolution you get for the homology of a free group. So the way I think of this is if I take a guy, if I have a reduced word W, and I weight it by a function defined on its range, because remember, everybody can be written in that form from the skew group ring perspective, and it belongs to the A component, then I think of this guy as the edge in the Cayley graph of the free group from W to WA, but then I weight it by this function F. And from this point of view, the boundary map is I do F times delta WA minus F times delta of W. So this looks like the boundary map in the Cayley graph, which is a tree, and therefore contractible, weighted by this function F. All right, and what is the idea? How do I prove that this is exact? I write down a contracting homotopy. I just write one down because it's not very long. And the contracting homotopy is basically the same contracting homotopy you would write down to prove that the free group, that the Cayley graph of the free group is a free resolution for the trivial module for the free group. What does that resolution do? Given a vertex delta W of the free group, what you do is you send it to the sum of the edges on the geodesic path from 1 to W, where the edges are signed by whether you use them forward or backwards. So I do the same thing here, but I weight by this function F. And the way I use semisaturated is that the semisaturated condition says that if F is defined on delta WA, it's also defined on delta W. And so it's the condition that guarantees that on any prefix of W, I can put an F in front of it, and it's a legitimate guy. F will always belong to the domain of any prefix of W. And so I can write down the same contracting homotopy, and it works. And I need semisaturated to write down that contracting homotopy. Otherwise, my function F will have problems. But that's the basic idea.
May I ask, suppose you have the partial action of the free group on some ring, right? Then is there a way of imitating this so that you obtain a free resolution on the cross product of the free group and the ring? So that will be the ring on which we consider the modules. You get a length 1 resolution over this ring of the original ring R, regarded as a module over this cross product.
Do you want to look at it as a bimodule or as a one-sided module?
One-sided. As here you are looking at as a one-sided, right? So the ring would be Z of X is a ring.
Right.
Which is also a module over Z of G, and Z of G is the cross product of FA with my ring Z of X.
Yeah, so I thought about such things. Of course, you would have to do semi-saturated, and it's a bit messier with rings.
So this would be like the idea.
So, yeah, I mean, it may be. I mean, one issue, one thing that I'm taking advantage of is that this ring is a subring of my groupoid, and so the 1xa, it kind of sits inside both the trivial module and the groupoid. And if I had a GeNo ring, I'd have to be a little bit careful. My feeling is that instead of doing ZG1xa, I would have to do something like ZG tensor, the domain of A. I think maybe something is possible. I didn't try it that hard because I didn't have that many motivating examples to do, but possibly. I mean, I did think a little bit about that. I was actually trying to work with bimodules because I really wanted to try to get it Hochschild, but it was a bit messier. The bimodule stuff is a bit messier than the one-sided. Yeah, I kind of had this weird hope that like if you had a quasi-free algebra and a partial action, semi-saturated action of a free group, on that maybe you might get a quasi-free algebra or something, but I don't know
Ah,
whether that's true
that's very interesting.
or something like that. But I didn't quite get it. Um, so let me just point out this resolution has length 1, so that means that the cohomological dimension of my groupoid is at most 1. If the isotropy of the action of the group on the space is non-trivial, then the dimension will be exactly 1. The dimension can be 0, though. If you take a finite acyclic graph, then the graph groupoid is a groupoid of a partial action of a free group, which has trivial isotropy, and that groupoid has cohomological dimension 0. Or homological dimension 0 and cohomological dimension 0. In fact, it's basically a semi-simple algebra, so everybody's projective. So you get matrix algebra. Or product of matrix algebras if it's not connected. So in any event, um, yeah. So the isotropy is trivial. You might get cohomological dimension 0, but if it's non-trivial, you'll get 1. I'll say a little bit more about that later. So you can think of this as an analogy to the fact that free groups have cohomological dimension 1. Of course, a free group is a special case of a partial action of a semi-saturated partial action of a free group. And the other thing is with this chain complex, we can very easily compute the homology by taking the coinvariance. In other words, tensoring with the right trivial module. And so here's the homology of this groupoid. We just apply it to our resolution and we get that, first of all, the homology vanishes in degrees bigger than or equal to 2. The homology in dimension 0 is just the co-kernel of, I'll explain what these maps are. IA is basically the inclusion of XA, and theta A star is induced contrariantly by theta A. So let me just write what these are. So IA is the natural inclusion of ZXA into ZX by extension by 0, and theta A star is just precomposing with theta A. So these are upper star. So this upper star, this is the same thing as theta A inverse lower star, by the way. Theta A upper star is the same as theta A inverse lower star. So I could have written it that way. I'm not sure. Maybe I should have. So anyway, it's something that you can write down explicitly as co-kernels and kernels. So for instance, you can use this to get the homology of a Deaconu-Renault groupoid. Let's say with exostone space and the domain Clopin. You get the homology is 0 in dimensions 2 and up. In the dimension 1, you get the co-kernel of the inclusion minus, so I'll write what these are, the inclusion of the domain minus the map induced by the local homeomorphism T. This T star is the sum of the theta upper A stars, and the H1 is the kernel of this. Now you can find this result, for instance, in Farsi, Kumjian, Pask, and Sims, a 2019 paper, in the case when the domain is all of X and T is surjective. But they only assume locally compact and totally disconnected. And they prove this using a spectral sequence associated to the cocycle. So they do a spectral sequence argument. They use that there's a grading on the groupoid. The homogeneous component of 0 is an AF groupoid, so its homology vanishes in high dimensions, in dimensions above 1, and that makes the spectral sequence collapse, and then they're able to compute something. But here, this is completely elementary. There's no spectral sequences or anything yet. So yeah, so that's the homology. And again, I don't need to assume surjective or totally defined. If I made X locally compact, I would need to add some conditions to be able to get it as a as a partial action groupoid, and I would get flat resolution. So it's a little bit more complicated if X is not compact. Let me just point out, this is kind of a side result that I still haven't put on archive yet because I'm trying to make it nicer. Um, um, a groupoid has homological dimension 0 when ZG0 is flat. In particular, cohomological dimension is stronger than homological dimension 0, so sometimes our groupoids do have cohomological dimension 0. And actually, basically, and the groupoid is called AF, or almost finite, if it's a directed union of compact, open, principal subgroupoids. Principal means all the isotropy is trivial, so there's at most one arrow between any two elements, so it's like an equivalence relation groupoid. And so I haven't put this anywhere yet, but homological dimension 0 is the same as being AF. So DG0 is flat if and only if it's AF. So in particular, for our partial actions of free groups to not be homological dimension 1, the groupoid would have to be AF, which it can be.
But this theorem is, I mean, do you need what you said before to prove the theorem? No, it's
totally unrelated. I just adding it in for context. Yeah, this is totally unrelated, other than the fact that it's helping clarify when you get dimension 0 in the other theorem, and that it can be dimension 0, because you can get AF groupoids as partial actions of free groups.
And for cohomological dimension 0, is there a characterization too?
Well, if the unit space is compact, I think it's probably, I should be careful on that. I think if the unit space is compact, it might end up being just the same thing, which I've been assuming. In general, cohomological dimension 0 is stronger. It's much stronger.
Yeah.
Because they're von Neumann regular ones, which are not semi-simple.
Maybe it's, semi-simple. Yeah, the algebra should be semi-simple.
But I'd have to think about the unidal case. But in general, it's not. Yeah. Basically, if the underlying ring is semi-simple and it's cohomological dimension 0, then it's going to be semi-simple. The algebra. If you're working over like a field or something like that. If we're working over Z, of course, it's a slightly different situation. So I just want to say a little bit about global dimension. I don't have that much time. So the global dimension of a ring R is the supremum of the projective dimensions of its modules. It's also the largest n for which xn of some pair of modules is not 0. And let me just point out, there's work of Peirce on von Neumann regular rings, which tells you if X is a stone space, K is a field, and X is second countable, then the global dimension of Kx is less or equal to 1. I mean, this essentially follows from Kaplansky's theorem that countably generated ideals in a von Neumann regular ring will be projective. That's essentially. But he also shows that there are stone spaces X for which the global dimension of F2 of X is arbitrarily large. So if you're trying to get the global dimension of an ample groupoid, you're going to want to put some countability conditions on X, or it could be very big. It can get big. So I'm going to look at partial actions of free groups on second countable spaces to have a chance of getting low global dimension.
Sorry with a stupid question. Isn't F2 a field?
Yeah, but now I'm taking the ring of continuous functions with compact support from X to F2. So I'm looking at a Boolean ring, basically. And Peirce shows you can get Boolean rings of arbitrarily large global dimension.
Okay, so but they are always from Neumann regular.
Regular, yes.
Flat, but not every module.
So the weak dimension is 0, but the global dimension can be as big as you like.
Okay.
Yeah, and so, these things, of course, are stone spaces on very large spaces. And, depending on the weight of the space, that controls sort of the global dimension, or at least gives a lower bound on it. Okay, so the theorem that I was able to prove is that if K is a field, then the groupoid algebra of this partial transformation groupoid for a semisaturated partial action of a free group on a compact disconnected space, which is second countable, has global dimension at most 2. I would really like to get 1, because that's what happens for graph groupoids. But the proof seems to make 2, and I have not been able to get around it. The key idea is that I can bound the global dimension of Kg by the projective dimension of the trivial module plus the global dimension of the unit space, which is where I need the second countable. So in our case, the projective module Zx has projective dimension 1, and because the ring is second countable, this guy has global dimension 1, and so we get a bound of 2.
Right. The 1 comes from the Z.
The 1 comes from the ZX from the Z, yes, and the other one comes from the fact that this is von Neumann regular but not semi-simple. So that's where the other one comes from. And so I only get 2, and I really would like to get 1. For graph groupoids, the global dimensions at most 1. Is this true more generally? I really hope so. I don't have any evidence to prove otherwise. Of course, the other case where we know it's true is if you do a total action of a free group. If you do a free group. A free group is an example of such a guy, and a free group has global dimension 1 over a field, and it's a semi-saturated partial action groupoid. But that's an extreme case. So, what happens in general, I don't know. More generally, if you had a free group acting on a semi-simple, on a finite space, you would also get global dimension 1.
Just one question. In the case of, say, there are many instances of augmented algebras or supplemented algebras, I don't know what sense, where you have an algebra or a ring which contains a subring, and the subring is also, say, left module over the bigger ring, right? So as in this case, Z of X or K of X inside K of the cross product. And in many situations, the cohomological dimension of this subring as a module over the big ring coincides with the cohomological dimension of the big ring. I don't know how general this phenomenon is, but it does happen. For the group ring, this is precisely the case.
Yeah, it's similar to what happens for a group ring, that if you're working over a field, then so you have to worry about the homological dimension, so the projected dimension of the supplemented thing, and then the global dimension of that ring. It's the same kind of thing. The next theorem, I think, answers your question. So there's a spectral sequence which controls it, which in the way you're saying. So first of all, you can show that when you extend the scalars from Z to K, the global dimension the projected dimension does not go up. So that's the first thing that you show. And then we really work with the projected dimension of KG0. So there's a natural KG module structure on home KG0AB. And then using the KG projectives are also KG0 projective in our context. You can get a KG module structure on X and KG0AB for any KG modules, A and B. And then you get a convergent spectral sequence, which tells you how to compute, in theory, X between 2 modules in terms of X from the trivial module, which is like cohomology, into X over the base ring KG0 of AB. So I think this is the kind of thing you were talking about.
Yeah.
And then so in particular, if you get above the dimensions where both of these are 0, then it's going to force this thing to become 0, because everything will collapse. So that's the main trick, and it's the same kind of trick you use for groups. You just have to show that you can define the KG module structure on the HOM and the X, and so it's not that difficult. It's similar to the group case, but technically there's a little bit more work to be done. But that's what we use to get the bound. Then you can bound when this vanishes in terms of when these two guys, when this vanishes and when this vanishes, and then as I said, the projected dimension of KG0 is controlled by the projected dimension of ZG0. Or you could just extend the scalars on my projective resolution, and that would be fine too, since my projective resolution ends in a torsion-free module. So. And so my conclusion, I guess, is so we're able to get a bridge between the partial actions of free groups and homology of ample groupoids. We can write down explicit short projective resolutions that lets us avoid spectral sequences, at least for computing homology. Of course, there's a spectral sequence for global dimension, but oh well. And also we connected groupoid homology in this last spectral sequence, or groupoid cohomology rather, with the X between arbitrary modules. And that's pretty much what I had to say.
Thank you very much. It was wonderful talk. you wonder about Hoshi homology, as you did, as you told, you mentioned. Do you expect to have some sort of a Burgiglia decomposition for the Hoshi homology, at least in this for these groupoids? I mean,
For which homology? Sorry, I didn't.
well, so suppose you wanted to compute Hoshi homology.
Oh, Hawkshield. So I think there's a paper of Misha Dokuchayev and Kripchenko where they use the inverse semigroup, but they could use the groupoid instead to look at the Hawkshield cohomology using that.
Spectral,
Yeah,
yeah.
yeah. I also had sort of some unpublished notes using doing this kind of groupoid stuff that I had sent to Cedric Bonaffi when he was asking me about how these things relate, which was from around the same time, but they were sort of unpublished notes, so I didn't put them in archive. But yeah, for Hochschild homology, they have a paper, and I think it's kind of a bit like groups. You can also translate between Hochschild homology and the one-sided ones. I didn't check this, but I believe you can do the same kind of tricks by using the conjugation action to go back and forth between the one-sided and two-sided stuff, so that X, Hochschild, and all these stuff I believe are going to all be the
you
same.
think so? Is it true that groupoid homology with coefficients in the joint action is the same as Hochschild?
Well, maybe Misha knows the answer to that, but I think, I think probably maybe you need your group weight to be slightly nice for cohomology. For homology, I think things are okay. For cohomology, things are probably more difficult, but maybe Misha can answer that since he has his hand raised.
Yeah. He has lifted his hand.
So maybe he has an answer to that.
So, Misha, do you want to say anything?
Oh, hello everyone. So very nice stuff. I have the following question. So I wonder how do you produce the spectral sequence? What do you use Grothendieck spectral sequence or?
Well, I did it as a double complex, but probably you could use Grothendieck spectral sequence if I was better in the ways of spectral sequence. I mean, I kind of do the standard double complex you would do with a group. So I think, like in your paper, I'm just looking at the inverse semigroup acts by conjugation. Acts by conjugation. The inverse semigroup has a natural action on the Hom by conjugation, and then you can check that it descends to the groupoid because it satisfies the relations. And then I build a double complex using the fact and exploit that projectives for the groupoid are projectives for the underlying ring, at least in my Hausdorff situation. And I get a double complex. But maybe I could have used the Grothendieck spectral sequence. Probably I could have, but I'm more familiar with the double complex. So I think most of the time a double complex or often can be replaced by a Grothendieck spectral sequence when there are two functors like that involved, but that's what I did, was a double complex.
Yeah. I mean, the Grothendieck spectral sequence does come from a double complex spectral sequence.
Yeah, but you need these Cartan-Eisenberg resolutions, and here I could just do the naive thing of resolving both ZG0 and A, doing projective resolutions of both, and then moving things along the Hom tensor junctions.
Yeah, thanks. Another question. So you start with a partial action of a free group, and then you speak about you work with homology of the partial action groupoid. So I wonder if there is a relation with the partial homology of the free group. So by partial homology of free group, we mean you take a module, say left module over the. So it is defined using partial group algebras, and so you would take a module over the partial group algebra, a left module, say, and you also inside of the partial group algebra you take a subalgebra, a commutative subalgebra generated by those idempotents which which appear in the Excel semigroup. And it transforms into a module of the partial group algebra by the conjugation action. Like we did, you mentioned our paper with Mikola and Juan Jacobo Simon. Actually, the idea of that conjugation action comes from this. And then you take the Tor functor, Tor B, let's call this algebra B, capital B, right? This subalgebra, this commutative one on which the partial group algebra acts by conjugation of the generators. Then we take Tor B, comma, our module, say V. And this how partial homology based on partial representations is defined. So
it would not surprise me if it gives the same. I mean, I didn't certainly look at it, but it wouldn't surprise me from what you're saying if you get the same answer as you do for the groupoid, but I didn't try. Do you know whether you get the same as you get for the partial transformation groupoid? Because I think the module, at least for modules that make sense for both of them, maybe, I guess the algebra of their modules are the same. I would guess that you get the same answer, but I didn't try.
Yeah,
that's a good question.
Because we know that you also mentioned Hochschild question about Guillermo about Hochschild homology. So there are papers about Hochschild homology of the skew products, right? So our paper with Mikola was for inverse semigroup actions, but there are also for partial actions of groups, even twisted partial actions of groups, or even partial actions of Hoff algebras. So, and there is a spectral sequence which converges to homology of the cross product, of the skew product. And this spectral sequence involves partial homology of groups and homology of the base algebra, Hochschild homology of base algebra. So the spectral sequence, so it's like spectral sequence relation between the two stuff. So I wonder if in the case of these actions of free groups, semi-saturated actions, if there is something more direct. So
well, I think you might be able to. Well, I don't know. It depends what you mean by direct. I would consider writing down an exact sequence more direct than the spectral sequence. Can you probably prove compute the homology more generally with a spectral sequence? Maybe one coming even from the co-cycle. I would guess so. But this has the advantage you can really write it down explicitly, and you don't need to use any technology. I mean, for the partial actions, semi-saturated actions, these are just actions of the free inverse semigroup. And there's an equivalence between actions of semi-saturated partial actions of the free group and actions of the free inverse monoid. And so you could really just work with, or free inverse semigroup. So you could really work with that, which is kind of like the Excel semigroup for this context. And, and that guy also behaves well homologically. So I suspect you could also compute it working with the free inverse semigroup as well.
Okay, so are you saying that if you have a semi-saturated action of a free group, then you relate the...
You get a regular action of the free inverse semigroup.
Géroux's expansion would be a...
Okay, his expansion gives you the free group, but this is a smaller than his expansion. It's tighter because it keeps the semi-saturated condition in. It's in between the full expansion and it catches just the semi-saturated actions.
Yeah.
But you can use therefore the free inverse semigroups module theory to also get a hold on this.
So that's a good idea, definitely.
So sorry,
okay.
Should I stop the recording?
So
it is after
thanks
10.
a lot. I'm done with my questions. Thank you.
Okay.
Okay, so let me see.